All right, I guess there's really no point in beating around the bush, but I'm not going to lie to you guys. I'm actually quite nervous about this. Why? Because this is all 15 cells fully charged. This is a high-powered test. So I learned from the last partial power test, I've clamped down the blower to this table that's, she may be ugly, but she's got a 100-pound cast iron base, which is why I use it. So that shouldn't move. There's a sandbag on top of it, so for safety issues. Here we have a frequency readout, which I'll explain later, current, and then up here is voltage on the top, and on the bottom you have the temperature of the ESC. Control circuitry is plugged in and it's set for full tilt. This is how you operate this thing. So this will ultimately be the console in the car, and this box, so obviously you get upholstered, assuming everything works and it doesn't blow up here, which is a possibility. So what you do is you first hit the anti-spark, which charges up the capacitors in the ESC, which is this button. Give it a couple seconds, and then you throw the switch. There we go. So she's primed and ready to go. Say a quick prayer, hope this doesn't go badly. I have a remote so I can stand a safe distance away from this thing. There we go. I'm going to try for about a 10-second run. I'm going to stand where if it fails, it's least likely to hurt me. Here we go. All right, that was 10 seconds. I have no idea what any of the gauges read. It seems to be functional. Let's see, the ESC temperature is going to climb here. Yep, it's up to 86.6. Battery voltage is down to 61.5. I'm going to get an oscilloscope because I want to see a different reading off the frequency there. Okay, so here it is, the second full power test. I've got the oscilloscope hooked up this time. It's a little bit different, and we are of course breathing through the air filter. That is probably important to note. I don't think it makes much difference, frankly, especially for this, but you know, I wanted to test it as it's going to be in the car. So let me grab my handy dandy remote, take a step back, and run it for about 10 seconds and see what we get. And that's it. The ESC is fried, people. Yep, ESC is done. Well, I'm glad we found out here as opposed to elsewhere. And because of my quick cutoff switch, we were able to save that. So we'll be taking the ESC apart and we'll see what went wrong there. And unfortunately, we're going to have to order another one. It's just the way of the world. Although this one should have a warranty because I'm not pushing it with its ratings. So we'll take a look. All right, well, that is what it is. Let's see what happened. All right, so we shot the beauty shots on Thursday. We blew it up on Saturday, and now it's late Monday night, and I'm finally getting around to shooting the alien autopsy. But, you know, I just wanted to say I've kind of hit that age where I have parents who are both having health issues, one considerably worse than the other, you know, and of course I've been raising my daughter for 10 years by myself, but she's been much more of an asset lately, so cheers to you, Sparky, thanks. That's given me more time to work on this thing. So as you saw, the ESC let go in moderately spectacular fashion, but it happened quick. It happened less than 6 seconds into that pull. I've sent an actual email to the company because this thing apparently has a warranty. Haven't heard back from them yet. We'll see what they say. I sent them a short clip of where it blew up and the specifications under which it blew up because we were measuring everything. Like I said, haven't heard back from them, but we'll see what they say. If I don't hear back from them, the game plan is I will take this thing apart and see if I can improve it. I'm pretty sure what let go was most likely some of the MOSFETs. It could have been something from the capacitor bank, but looking across the top, nothing appears blown, which is usually where they blow. But then again, it happened in 6 seconds. It's probably not enough time for the vents to let loose. So if we end up going that route, we'll go into it. That'll be a separate video. But whatever, it's fixable. We know it's fixable, but we also know that this thing works. So let me let me say something first. Okay, this is dangerous. This is really, really dangerous. You know, I've had people post comments, why don't you get bigger batteries? Which I might actually need to get bigger batteries, but not because we need more power. We need more power, or we need the same amount of power for a longer period of time. These battery packs, or this battery pack, these cells combined are capable of putting out over 48 kilowatts. That's kilowatts. They can do that for 20 seconds. That's more than enough power to kill you. And if that doesn't kill you, you know, this thing could explode. And you saw how I had a shot bag on it. This thing is no joke. You saw the corner of the table. That table weighs about 100 pounds. It has a cast iron base. You saw it actually lift the corner of the table up off the ground. We're talking about some pretty serious power here. It is dangerous. The reason why I say this is not a how-to guide. If you choose to do this, you're doing it on your own. There's no liability here at all. So having said that, I'm also going to gloss over how all of this works, but I'm not going to go very specifically. And the reason why I'm not going to be very specific about everything is if you can't figure out how to do this based on what I'm going to tell you, then you may want to rethink trying to do this, because like I said, this is actually highly dangerous, and it frankly does scare me. So anyway, so the purpose of this whole box is it'll be my center console. Right now my center console is the air to water intercooler tank in the LTD. Where most of these projects tend to fall down is that they don't have a car to test things on. Well, guess what? We have a car to test things on. So let me go through basically sort of a block diagram of what this thing is. Again, you know, this will be upholstered eventually. There'll be a flap here, probably a cooling fan to bring things through. People asked how I was going to cool the ESC, by the way. That's how. Just that simple. Just a fan. In fact, this is what holds it into position, basically. There's T-nuts on the backside. That's really it. There's not much to it. This fan, unfortunately, doesn't really move a whole lot of air. I did get a second fan in, and that second fan, in the reviews, it got 5 stars, but in the reviews, it always said it sounds like a jet engine. So that's kind of what we want here. We want as much cooling on here. But as you saw, it didn't get hot anyway in that short amount of time. But nonetheless, in a car, inside a console, you know, more air the better. I'm not really worried about noise because, you know, that's going to pale in comparison to all the other racket that's going to be going on at the same time. So that's that. So you saw the gauges. Actually, before we go into that, I wanted to talk about how I ended up making this power distribution. I did mention in a previous video that the 10 gauge wires that I made that wonky harness out of, they got hot. They got uncomfortably hot. Well, you know, eventually this thing's got to be functional in a car, and it has to be easy to function, relatively speaking. So what I did is I took a solid hunk of Delrin. It's down here. You know, I milled out these copper pieces. That's been, you know, I have to tell you, I hate machining copper. If you've never done it and you don't know why, it's because copper is very grabby. It's very gummy. And when you're doing small, fine precision work like this, you know, I mean, this isn't that precision, but when you're doing small work like this, you're using a lot of small drill bits and such, so they tend to break off. And, well, that happened a couple of times. So what do you do when a Chinese center drill breaks off in your copper? Well, you send a piece of American carbide after it, and it eats through it like there's nothing there. And that's what happened. So it actually happened to me twice on this. So it took a long time to mill this block out. But the great thing is that it works extremely well. It's very robust. There's absolutely no losses except for the battery cables themselves. There are no appreciable losses. This is a Marine battery cutoff switch. Apparently it's rated at something stupid like 1400 amps, though don't know how much I believe that. These brass posts that are attached on the back. I actually made those out of a 1/2-inch brass stock to screw onto the back of the studs, because there's really no good way to do a sharp 90-degree turn, and this seemed the most efficient thing to do. So that turned out pretty cool. Didn't video that because time and everything else. And the other thing that I noticed is the anti-spark cable had a relatively small, I would guess about a 2-watt resistor in line. So I cribbed this thing from, believe it or not, an old Wurlitzer amplifier from a Wurlitzer organ that I have kicking around, don't ask. Because, if you do the math, you're going to pull like 50 watts through that thing, most likely at least. So it was grossly underrated. Even though it's a short duration thing, I figured, I might as well overbuild it because there's parts that are underbuilt. So that took care of all that, and this turned out really, really well. This whole thing, it's not even screwed into place yet, and it doesn't really move. Just the cables and everything hold it pretty tightly, but it will get all screwed down. So anyway, so that was pretty cool. That was quite a neat process. I think the whole thing is kind of turning out really nifty. As you saw, we had a bunch of instrumentation on this thing. So this thing that you saw, I'll only let you, I'll only click it on real quick. So the top is the battery voltage, and the bottom is the temperature of the heatsink of the ESC in Fahrenheit. So, American, so that means, we use a system clearly different than everybody else on the planet. So that's what that was reading. So again, voltage, you see voltage drop. You saw the temperature didn't really rise a whole lot. So the other things that we did was we had current on one of these cables through a looping ammeter, and we also had frequency. Now the frequency is really interesting. Now there's this thing, where is it? It's in here somewhere. So this little tiny thing is basically a comparator made with an operational amplifier. I could have made it myself, but for the price, they sell these things, and for the price, I couldn't have, pieced together the parts for what I paid for this thing, so I just bought it. So basically, you can take a wire on any of the inputs, any of the 3 phases of the motor. It just fits nicely inside the 8mm bullet connector. It just kind of latches in there. And what this does is you don't really need this thing, except the problem is the voltage is going to be all over the place, and there's going to be a bunch of noise and everything else. So this definitely does help. It also brings it into more of a normal thing. But anyway, what I figured out was by applying a constant related to both time and the number of poles of the motor, effectively, if I take the measured frequency, multiply it times 20, that gives us actual motor RPM, which is something we really need to know, right? Because without that, we don't know where we are in the compressor map. We're just going to be basically pissing in the wind. And I don't like that because your pants get wet. So anyway, so here we are. So the motor survived, by the way, the failure nicely. Because it died so quick, and this is one of the reasons why I think it's actually one phase of the MOSFETs that failed, because it was still making some noise. You could hear it. And that's it. But the motor wasn't turning. But because the impeller stopped so suddenly, even though I put Loctite on our little hex drive bolt is still in fantastic shape, but it did actually back out. So it did what it was supposed to do. So that's awesome. That's worked like several times now. Not that any of the incidents we had would have been destructive. So I'm just thrilled mechanically the thing works. What I am concerned about is that in the first test that you saw, we only hit 26,000 RPM. Then in the second test that you saw, we hit 27,000 RPM. Again, look at the frequency and multiply by 20, and that gives you actual RPM. So at first I was concerned about this. I was concerned about a lot of this, obviously. This oddly enough didn't quite bum me out as much as I thought it would, because the bulk of it works. This is replaceable. Everything else that's important actually works just fine. So yeah, it's going to cost some money, and yeah, good opportunity to show for Patreon support, Patreon, however you want to say it. Patreon, I don't care. But, hey, if you're fortunate enough to still be working at this point in time and this stuff is valuable to you, go ahead and, pitch in a buck or two. I'd greatly appreciate it, because it does help offset some of the cost of this stuff. So anyway, having said that, let's go through sort of a block diagram of how this works. Okay, so let's get our little speed sensor out of the way. This, by the way, is my test trigger thing, and it really is just goes onto this little perf board here. This little perf board, there's actually not that much going on here. So in the back where you can't quite see it, there is a buck converter. It has a USB port on the side, and that's for auxiliary stuff. In this case, I'm using it for the operational amplifier, but I needed a 5-volt source anyway to power these two servo controllers. So basically, how does it work, right? So a lot of people, by the way, have said, are you going to put some kind of staging into this, or is it just gonna, are you just gonna let it go, you know, full power? What are you gonna do? Well, I see no reason to stage it. We should never end up in the surge zone. We should never end up there. So you might as well take all the power you can get, right? So in this case, it's on and off. And really all this thing does is it switches between one servo controller and the other servo controller. So this is your base servo controller. This thing needs to see a receiver signal in order to function. So this is putting out that 50 hertz, I think, what was it, 1 millisecond pulse, meaning, okay, there's a receiver connected, but guess what? The motor's not turning. So what this top one does is whatever I have it set to is where it goes when you hit the button. So basically, the only thing happening here, it's really dirt simple, is there's a small 5-volt relay under here, and it just switches the signal from this servo tester to this servo tester. That's all. And it works perfectly because I figured that a small relay is going to switch fast enough to be at least inside of one cycle. And as it turns out, it does. And as it turns out, the ESC, it's not enough to freak out the ESC, and it works perfectly. It kicks in, it works beautifully, as you saw. So by the way, I was powering this whole thing with one of these little batteries from the small DIY turbo contraption that we dynoed on the Harley that was really supposed to be a vacuum pump. But anyway, it's taking the place of the 12-volt source that we'd be getting from the car once this thing is installed. So where do we stand performance-wise? Well, that's a good question. Both runs, the first one and the second one right before it blew up, peaked at over 20 kilowatts. That's 20,000 watts. In fact, the second run peaked at over 22 kilowatts. And as the run went on, you can see that the battery voltage was depleting, but it kind of leveled off at 49 volts. So at 49 volts, that seems to be sort of our holding steady point. And at that point, we're at about 13 and a roughly 12 and a half to 13 kilowatts, I would say. So that's good. That's a lot of power. The point that's concerning, and one of the reasons why I'm glad we have this little operational amplifier circuit in the mix, is that we can see the RPM. And in the first pull, the impeller was turning at 26,000 RPM. In the second pull, it hit 27,000 RPM. And that's probably because the batteries warmed up just a little bit and they were a little bit more efficient on the second pull, which seems counterintuitive. But these batteries do like to be warm, they just don't like to be hot. So, in fact, they're going to suck in the cold, frankly. So, why only 27,000 RPM? I was thinking, oh, geez, you know, maybe it is a great opportunity to upgrade this thing and lower its internal resistance. And that probably is true. All those things are probably true. Probably will see a little bit more performance. But the more I thought about it, the more I realized, hey, wait a second. This is a centrifugal compressor. This is not, you know, I'm used to playing with positive displacement blowers. So in a centrifugal compressor, you know, just like we're not going to be in surge at any point, guess what? I think we walked off the other way into choke. Now, what happens in choke is that there is not enough back pressure and there's too much flow. So we had too much flow, and, you know, based on what I read, you know, it seems that the flow goes supersonic and it chokes it off, and the power to turn goes up exponentially. So what does that mean in the car? Well, think about it like a vacuum cleaner, right? So you have your shop vac, and if you cover either the discharge or the inlet, you can hear the motor spin up, and it sounds like it's working harder, but it's really not. That's why it increases RPM. It basically is working less hard at that time. And the electric Vortec is really not a whole lot different. You know, if you look at the compressor map, there's a reason why it has the shape that it has, and that's because it does require back pressure to limit some of the flow so you don't walk off that choke cliff, which is pretty much where I think we were. So that means, you know, we could realistically see, what, 35,000, 40,000? I have no idea, which is why we need to put this thing in a car. But that's going to be exciting to find out. So that is pretty much an overview of where we stand. As you can tell, the blower is getting ready to go in the car. That's another great thing. And then, you know, depending on if the company backs their product or not, you know, we'll see what we're going to do with this. But, you know, it's coming up real soon, as you could tell by the beauty shots from the beginning of this video. It is a gorgeous thing. It's got everything it needs to be bolted in. It's going to be the easiest blower mount I've ever built because, hey, there's no belts to line up. I can put it anywhere. And it's actually designed to fit exactly in one spot. That'll become clear when I put it in the car. So there you have it. So far, so good for the most part. I mean, when you're doing stuff like this, you know, fire is inevitable, really. So anyway, thanks for watching. Stay tuned and subscribe. More to come.